Hello class, in this session we're going to talk about the digital version of electronics. All the while we've been studying about analog and electronics. We talked about transistors and amplifiers and oscillators and p-n junction diodes. Now we're going to talk about the digital version of electronics. When I have an LED bulb, I could even have that has brightness control. I can have it on off, or I can have it dim or go bright. It's all analog. If I have a light sensor, I can either detect low light, medium light, or high brightness, or completely darkness. If I have a temperature sensor, I can detect low temperatures, I can detect high temperatures. If I have a potentiometer, I can set the position from 0 all the way till maximum, any value. And all these values are analog values. But if I have an LED, it's either on, it's off. There is no value in between. Such a value of high or low, on or off, 5 volt or 0 volt, is digital version of electronics. And this is what we're going to talk about in this next session. So we will be talking about this in reference to the base of numbers. When you talk about the number system, you talk about base 10, decimal numbers. So you have 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And those numbers can be expressed with a simple 7-segment display. But in order to get the 7-segment display to light up, if, for example, I have these 2 segments lit up, I can see the number 1. If I have the segment on top, on the right, middle, left, and bottom light up, I would have the segment 2. Each segment is either on or off. Such a value as an input to this 7-segment display would be considered as a digital input. So I give a digital input, I get a display that's showing a decimal number. So a binary number, zeros and ones as an input to all these pins, and I read out a decimal number that's a number that could read from 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. And in this case, that value is a decimal base 10. So we don't not only have base 2, which is binary, 0 or 1. We have base 10, which is 0 to 9. We also have base 16, where it's 0 to 9. Then you have A, B, C, D, E, F. So that's hexadecimal. So we will look at this in detail, but let's start with the basics, 0 and 1. How do we express 0 and 1? 0 is off, 1 is on. Why do I have a need to study about digital electronics? Reason being, everything from your cell phone to your computer works with digital electronics. Let's look at a simple requirement. For example, I have a voltage rising from 0 to maximum and dropping back to 0. How will that read? How do I convert that value into a decimal, into a binary value? Let's look at a conversion. Let's look at a circuit. Now I have a voltage ramp. It's a sawtooth wave, they call it. Looks like a sawtooth. It starts from 0, goes to maximum, and then drops to 0, again goes to maximum and drops to 0. This is a sawtooth input coming at 50 Hertz. Plus you also have another reference voltage which is divided. And this method is called, this is just using voltage dividers to have the voltage divided from 0 to, this is 0, this is 7 volt, and this voltage is divided across to so many operation amplifiers. Okay, now each operation amplifier would detect this rise in voltage and would turn on, and with this turn on pattern will give you through these XOR gates an output of 0 if the voltage is 0, and it'll get 1, 1, 0, 1, 1, then it'll go 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. In other words, the variation, if you look at how you convert binary numbers to decimal and binary, you would remember that there is an incremental fashion that the numbers move. For example, when my binary numbers move from 0 to 9, then the next digit gets incremented. It becomes a 10, then it becomes 11. So then after that, from 11 to 19, it's 1. Then when the next digit, first digit goes to 9, I increment the next digit to 2. The second digit starts incrementing from 0 to 9. In the case of 99, then I go to 100. So talking about the base numbers, I go from 0 to 9, I increment the next number. But in the case of decimal, I go 0, 1, I increment the next number. So it's 0, 0, 0, 1, 1, 0, 1, 1, if it's 2 decimals. In this case, we have 3 decimals. It's low or high. So looking at the bottom pin, yes, it switches states. It's going high, low, and this is half the sequence. In other words, one high and low, this goes once high. Then looking at the next one, this once high and low, it goes once high. In other words, it's half the frequency as it goes up the ladder. Thus, I'm able to looking at reading this value, either it's LLL or HHH, the lowest value of 000 to 111. I'm able to convert this value of 0 to the rising 5 volt or 7 volt into an analog value, into a digital value of zeros and ones. This is a simple concept. Let's look at this in detail with a little practical demonstration. Let's look at the simple method of converting a binary decimal number into binary. The number given here is 266. The simple method is to divide it by 2, and you get a difference. You divide it, and what do we have as a reminder? You put that. For example, it was divided, it goes 133 times, remainder is 0, put the 0 there. Again, 133 divided by 2, you get 66, but the remainder is 1. You keep dividing it till you go down to the last digit 1. Now, to convert this into binary, you read it from the bottom to the top. So it's 1 0 0 0 0 1 0 1 0. That number would be the binary converted value of your decimal number given. This is a simple example, and you don't have to struggle to do this way. And these days you have scientific calculators in your hand. All you have to do, feed the number 266, set the base n on your mode of your calculator, and shift it around. You'll be able to get the same value in a matter of seconds. But it's good to learn it the manual way, because that's how you start. Let's look at it with the scientific calculator. Yes. So the number 266, if I convert it into hexadecimal, which is base 16, it's 10A. In decimal, it's 266. And in octa, which is base 8, it's 412. And in binary, as we converted earlier, it's 000, which is not considered. So you have the 1 bit, first bit here, 1 0 0 0 0 1 0 1 0. So this number in decimal is equal to this number, this number in binary is equal to this number in decimal. Does it sound complicated? No. Okay. If you do not understand it, you could try using your scientific calculator to convert it, or try this long division method to convert your decimal numbers into binary. You can practice it. There might be a question in examination that might ask you to do it, and the best way to do it is dividing it by 2. The same thing applies for base 8. Divided by 8, put the reminders around. When you divide by 8, if you notice, your values on your reminder will never be greater than 8. Your reminder, for example, in base 2, your answer will never be greater than 2 on your reminders. So you see the values is always 0 or 1. So when you divide it by 8, and if you've done it properly, your values will not be greater than 8. So your highest value will be 0, 1, 2, 3, 4, 5, 6, 7, 8. Again, the next digit will get incremented. It will never be greater than 8. So if you've done it right, this method will work for decimal, octa, hexadecimal, and binary conversion. Yes? And please try this method out. Work out a couple of problems. You'll understand how the early engineers worked with paper to convert values from one feed to another. Okay, this could you can try any more numbers. Example, let's take let's clear this out. Cleared out, and let's say the value 255. Look at the value 255. All the numbers are 1 in binary. In octa, it's 377. In hexadecimal, it's FF. Why FF? F is the highest value you could have in base 16, considering 2 bits of data. I mean 2-digit data. Yes. So when you want to convert that into bits, yes, it will be 8 bits of data and all ones. Yeah. So what is bits? A bit is 8 values, and that makes a byte. So FF is 1 byte of data. So 8 bits make a byte, and 1024 bytes make a megabyte, then your kilobyte and your gigabyte. That's how you talk about storage. Now, what do you talk about? Why do you use binary? If I want to store a value 256 on a memory card, the number that's going to be stored in memory card is going to be the numbers 1, 1, 1, 1, 1, 1, 1, 1. Reason being, that's how a memory card reads values. It has zeros and ones. The moment you look at digital electronics, it's always zeros and ones. So converting this value 255 that we understand into zeros and ones is what computers do in converting decimal to binary. So why do we need hexadecimal? When your computer needs to process a number, it can process it as zeros and ones. To make calculations easier and when you have powerful processors, they convert it into hexadecimal to do the processing. We need to understand that in a little more detail. Why, when you have more bits, when you have a value, a base value, it's much easier to have large values of data truncated into smaller numbers and to be able to calculate it. So computers convert everything to hexa and process it. For example, you talk about the early generation of microcontrollers and microprocessors. You talk about microprocessors, the 8085 and the microcontroller 8051. They all work with hexadecimal. The reason being, that's the language that the chips work on the arithmetic side of logical operation, arithmetic and logical operations. When it comes to storage, it's binary, zeros and ones. Why this complication? You need to understand what the forefathers of engineering have gone through to understand their achievements and what they've done for us in the last few years. With this conversion, let's go back and have a review when we do the next topic, and we'll come back to review more. If you have any questions, feel free to drop a note and I'll be able to answer them. Thank you and have a great day.